And next up, we have Simon Schmid from Edge and Node, who will be discussing new use cases and benefits from using subgraphs.
Hello. Do you hear me? Is it good enough? Nice. Woohoo! That works. Yeah, busy week. Thank you so much for taking the time to still come here and ingest some information. I hope it's useful. My name is Simon. I'm Developer Relations Manager at Edge and Node. That's one of the core dev teams that is working on the graph. And in this talk, which is a new talk, I quickly go through this idea that was once coined, I think, 1 year ago by Brandon Ramirez at the Graph Day. And it's going about the subgraphs into read-oriented rollups. It sounds a little bit weird, but we will build it up over time. So just a quick recap, what is the graph today? So it's a PDF. That is a GIF otherwise. So like the graph is basically taking that mess of marbles and organizes it, and that's what the graph does on data, of blockchain data. So it's very well known for this middle layer in between a front end and the contracts as the data layer that provides the data for these front ends in a quick fashion. So it indexes the data on the blockchain, prepares it so that the front ends can quickly use it. Well-known dApps like Uniswap, Analytics, for example, uses it, and much more. So it's actually a little bit an industry standard for that specific use case, like a front end that has data needs and needs those data through the graph. So as I said, like we also talk about the graph being the data layer of Web3. So the vision is really to become like across all chains and all protocols to have this data layer. And the graph is not just like a service provider. The graph is a decentralized network where we have currently 281 individual indexes across the world, bunch of delegators, bunch of curators, and 1,000 subgraphs deployed to more than 1,000 subgraphs deployed to this decentralized network, so that we can really create access that data. And up to today, we have almost 3 million GRTs and query fees claimed on that decentralized network, so that query market is working, and that leads to truly decentralized data. Like the data that is on the graph is open and accessible for everybody. So that's the graph. Quick recap. So then let's go to this read-oriented rollup. So what is this, and what are subgraphs anyways? So a little bit more technical. A subgraph is basically a curation function, so that we can say which information on the blockchain is interesting and how do we want to store it, and then store it in an index so that we can later on consume. So the data comes from the blockchain. It usually just starts with the blockchain, gets into mappings, which are written in assembly script or Rust now with the substreams, the new technology, and then stored in a database, and the mappings can also access that store, and in the end, a consumer can query it. So it's very simple data flow. In my presentations, here, when I click, there is like it's a magic stick coming, because I think the magic lies in the assembly script and in the Rust. Why? Because the language that we write the subgraphs in, it's assembly script or Rust with substreams, and that is Turing complete. Turing completeness means that we can code everything, like that we can code with Solidity or JavaScript or TypeScript or whatever, like Turing complete general purpose language. We can code into the subgraphs mappings. So, for example, we can have a Merkle tree prover that checks in the subgraph if an entity belongs to this Merkle tree. Or we can have like some CK proving algorithms that would be too hard to run on-chain, can run in a subgraph. Or even like I saw a side project from someone that created a synthesizer inside of the subgraph that, depending on the block an NFT was minted, created a different kind of music, all happening inside of the subgraph. So the interesting thing is here we can use that technology to run quite complex or like expensive computing that would be too expensive on a normal network or especially on-chain in a subgraph. So that's very cool. That already gives very cool use cases. And then 2 years ago, this guy, Denison, he runs Tally, he played around with this idea of like, oh, wait, so when we can have like all this logic inside of a subgraph, what can we then build with that subgraph? And he came to this kind of meta idea of like, hey, we can have a blockchain into the subgraph that connects with stuff on the main chain, or like even he talks here about Ethereum. I think gas prices were lower back then, but we can also think of Gnosis or Polygon or whatever that then just trigger stuff in a subgraph. And the code actually in Solidity to facilitate this is like this. It's basically, we have a contract, it's called the data edge. There is a specification about the data edge. You can read it in the GIP. I will later on also link the slides. And then that just has one function, the fallback function, that's always called when we call that contract with a function that doesn't exist. And that's it. And it does nothing. But what happens when we call that function is like that everything, like all the call data that we send to that function gets stored on chain and can be indexed by the graph. And that's how they started to build that social network on top of it, because they just send a JSON that says like create post from blah content X. And the subgraph was able then to build a completely database that was displaying that data. So that was fun in a way, and it's interesting to think about. But it's also like, I don't know, yeah, let's see how important that can become. So what's basically happened is that the logic moved from the blockchain to the subgraph, to the mappings. But actually, so this is the first primitive. So we have like Turing completeness in the mappings, in the subgraph, we can run big code. So the next step is the off-chain data. Now it gets interesting. So the graph has the possibility, or the graph network, to also index data from IPFS and RWeave and then add it to the mappings and put it into the store. So now we can mix and match. So in the social network from before, we can upload that post just to IPFS and then anchor it down to the data edge. It gets then indexed, stored, and we can query it with everything that we have. But that's not all. Like, the team at Edge Node started to create this. So like the graph network, there are multiple gateways across the world, and then multiple indexes across the world, and queries go to the gateways and then to the indexes. What's very important for every kind of stakeholder of the graph network is we want to know like what's the quality of service, how do these indexes perform. That's kind of something that gateways know in a centralized way because they have like Web 2 connections. And now, they worked on this idea of republishing that data. So how does it work? Every gateway that is there has logs. They know, like, OK, I sent this request to that indexer. It took that long, and that's it. And then they put it to this data science pipeline, and Red Panda materialize. That's not my thing. But in the end, there is a cron job that uploads that big data. It's a lot of data that is there into IPFS, anchors back with OpenZeppelin these things that we can trigger on OpenZeppelin to write on-chain, and then the graph indexes it, goes back to IPFS and has it. So now we have a network quality of service or Oracle subgraph that we can query and see like which indexer has which quality of service, which subgraph performs how, and so on and so forth, all in a very decentralized way. We can even think about other use cases that come here, like, I don't know, it could be any Web 2 data, basically. It could be hotel rooms that are free. It could be airline seats that are free. They all can be the same, uploaded to IPFS, anchored on-chain, indexed by subgraph, make it available through the subgraph. Or also, like, a very interesting use case would be we can have weather stations that do the same. Like, we have hundreds of these weather stations. They all upload that data, anchor it on-chain. The subgraph gets it, combines it, aggregates it. And then we have, like, a current weather or, like, a very good information about how the weather is currently look like. And that all builds on top of what's already there with the graph. Like indexes are already there, so we don't need to even think about infrastructure, because if the subgraph is deployed and IPFS deployed, the indexes index it and make it available to query. And the other stuff, also payments, indexes get paid to serve queries. Curators can curate on subgraphs in order to participate in the query fees. So the whole power of a decentralized network with all the incentivized different stakeholders can be used to also publish Web 2 data. And now even this week, we launched this new billing thing on the graph network. Before, like we had to bridge GRT to Arbitrum in order to pay for the query fees. Now there is a super simple subscription thing where we can just say like, okay, so that many queries, boom, per month, that's it, deposit USDC, and then it just runs. So if anybody's interested in running that, find me, we can help you. But now we got even one step ahead. So now we have all this data. We saw like it's blockchain data. We can even calculate on blockchain data maybe more complex risk parameters or something like that. We have the off-chain data, that's the on IPFS, but now we can bring it even back on-chain. So how would that work? So we have the blockchain mappings again, as before, and now instead of just a consumer that might be front-end or a data science application, we have an oracle that brings it back. Chainlink launched the Chainlink functions, I think a month ago or two, and at this hackathon and also like during the FCC, saw different examples. There's actually a live code example how to use the graph in Chainlink functions to bring data that's on the graph pre-computed or prepared for whatever use case we have back on chain. Also, Gelato has Web3 functions that can do the same. So now we have the whole flow of data. So to finalize and talk about this read-oriented rollups and why this model that I just explained kind of fits into this narrative is like when we have a rollup, like in this example, a CK rollup, we have a state that's created on the CK rollup, then it's proven and put down to L1, and transactions can also go up. Like there's this interaction between. And now when we have read-oriented rollups, it's a little bit similar, but like the state comes up, it will be pre-computed or computed and changed on the L2 or then in the subgraph, and then can be rolled down again with the oracles to L1. So that's where this read-oriented rollups idea comes from, and that's kind of explained in these things. So at the end, I just quickly want to go into this one big topic, which is probably the elephant in the room when we talk about oracles and data in general. It's like verifiability. Like, how can we trust the data that we see? It's one topic that is very core to the vision of the graph, that really this idea of like, okay, if you see Web2 data, do we know if we can trust it? If we see data from a centralized data provider, how do we know if the data provider does actually giving us the right data or not? So if we, I don't know, go to a centralized data provider and ask for a price of a certain token, the centralized data provider might give a wrong quote in order to game the system a bit. So with the graph, with the current implementation, it works like this. Each indexers need to stake. Some indexers stake more, indexers stake less. Whenever, then there is two steps. So first, they do indexing. They see data, they index it. They compare, like indexers compare with each other, like which data that they see. It's so-called proof of indexing. So they hash, basically they hash the data in set intervals, we call them epochs, and put it on chain so that the others, so that we can compare. And that's one. So we see, okay, the indexes saw the same data. And then the second, obviously, is like then the querying. So the proof of indexing helps with, I would say, faulty software, because they can compare, did we see the same data? But if a malicious indexer, for example, wants to return wrong data, like consciously, then it would happen at the query layer. So what indexers do is, like with each response, they send a so-called query attestation. And with that attestation, we have a response to that query and that attestation. And later on, when we can prove the indexer wrong, that response to that query was actually wrong, the indexer can get slashed. And that's how these oracles also work. So they take the response, put it on chain, but also the attestation. And also with Chainlink, we take then the responses from different indexers and combine it and see if there's any difference. And if it's all good, we put them on chain with the attestation. And if we later on see that something went wrong, we can slash the index. So that's not perfect. It's kind of optimistic. So that's where actually we can go to the future. And there is the one core dev team is particularly at the graph, Semiotic from Los Altos. They work on this big problem of called verifying indexing and querying, kind of having the whole stack, like the indexing, really verified with these CK proofs of what they saw. That's also a little bit below above my brain level, but like that's kind of the end goal, to really have like, I receive a response from a graph indexer, and I can check the response with the attestation directly without needing to trust. So that's where we're headed, and yeah, hopeful we will achieve that state soon. But until then, thank you so much for coming here and watching that talk.